students to this video, and in this video we are going to talk about linear transformation and some properties of matrices. Okay, so first of all, you see, we suppose that we start with two bases, okay, x1, x2, xn and y1, y2, yn, okay, are bases of vector spaces x and y, okay, spaces x and y, right. Now you see, you start with for any a, so we start with a linear transformation a from x to y, right. So this, you see, for any a in this linear transformation, this determines, okay, determines a set of numbers such that, you see, a acting at xj, right, is equals to, see, a for any j, let's say you fix a j, right. So for any j, let's say 1 less than equal j less than n, right. Okay, so you fix any, sorry, I should write it as am, huh? So for any j between 1 and n, a of xj is an element of y, right. So you can actually write it in terms of summation a I j y I, and I is varying between 1 and m, right. So it will be a linear combination of yi's, y and I lies between 1 and n, right. So that we can always write it, and this holds for all j between 1 and n, right. Okay, fine. So you see, what is happening is this a, if you want to write down, okay, so we can actually visualize this as a rectangular array of m rows and n columns, called, which we are calling as a m cross n matrix. So therefore the matrix A, we can visualize it as this. You see, a 1 1, okay, a 1 2, a 1 n, a 2 1, a 2 2, a 2 n, and the last row a m1, a m2, a mn. Okay, so this will be your m cross n matrix, okay. So essentially what you have is, if you have a linear transformation a from L to from x to y, okay, then a can be visualized as a set of m cross, so as a matrix which is a m cross n matrix, right. Okay, so you see the so if, let's say, x is, can be written as this summation cj xj, okay, because I'm starting from x in x, and so x can be written as the sum of xi's. The linearity of a combined with, let's call this 1 1, okay. So essentially the representation of a shows that a of x is nothing but summation, okay. See, x is nothing but summation cj xj, right. So A of x can be written as summation I equals to 1 to m summation j equals to 1 to n a ij cj yi yy, and therefore the coordinate of a of x, the coordinate, okay, of a of x is what? This sum part r summation aij cj, okay, and this basically we write it like that. So essentially this is our representation. So given a linear transformation, we can actually write it as a matrix, huh? Okay, so one question, so check. So given a matrix, let's say given a matrix A, which is a matrix, m cross n matrix, can one write it as a okay, can you represent it as a, let me put it this, can one represent it as a linear transformation? Trivial question, right? So anyways, you please try and answer this question if you can do that. So essentially what I'm trying to say is this: given a linear transformation, there's a matrix, or vice versa, if there's a matrix, there's a linear transformation, right? Okay. So they are basically the same thing. Okay, so now the question is this: why are you suddenly interested in this? Because matrix plays a fundamental role in our study of ODEs, right? Which we are going to see in later on. So okay, so first of all, anyways, you guys already know this matrix is of size m and cross n, means m rows. So this is m rows and n columns, okay, columns, right? Now the thing is this, we are going to introduce some notations which we are going to use, okay? So definitions are notations. Definitions, let's just write it as definitions, okay? Definition A. So essentially if aij, this is 0 for 1 less than I, okay, not equals to j less than equals to n, then A is called a diagonal matrix, right? Called a diagonal matrix. So essentially every element of the set, every element of the matrix except the diagonal elements are 0, okay, and if and in addition if aii is 1, okay, then we call it as a identity matrix. Then we call it identity matrix given by in, okay, m cross n, okay. So please remember these are the notations which I am going to use throughout the lecture, okay. So I am not going to explain all the time. So a m cross n, if I am writing it like this, is basically with aij equals to 0, it's a diagonal matrix, and if aii's are 1, that is the identity matrix, which will be always written by as I m cross n. Clear? Okay. So without, if it is clear that the matrix which you are working with is a m cross n matrix, then it will be always written as I. Okay. Now the thing is, we will call a matrix this thing symmetric if A equals to A transpose. A matrix is symmetric if A equals to A transpose. Okay, and we will see the trace of the matrix. Okay, so the trace of a matrix A, right, we will denote it as TR of A. Okay, again I am not going to repeat myself. TR of A is defined as the trace of the matrix, and which is nothing but the sum of the diagonal elements AIIs equals to 1 to n. Clear? Okay, so that is there. Okay, so that is more or less the I mean all the definitions which you need. Okay, and now I am assuming that you know some properties in determinants and all that we are not doing it right now. Okay, right. Now another simple fact which we need to know related to matrix is this. Okay, so you see, consider this system, the linear system of n equations in n unknowns. Okay, unknowns. So so basically you are looking at a set of equations. How does the equation looks like? A11 u1 plus a12 u2 plus a1n un, okay, equals to, let's say, b1 a21 u1 plus a22 u2 plus a2n un equals to b2, and it goes on like this, and lastly an1 u1 plus an2 u2 plus ann un equals to bn. Let's just write it like this. Okay, where aij, this set, clear, and bi 1 less than I comma j less than equal n are given real numbers and ui's are n unknowns. Okay, so if you consider this system, let's call it the system star. Okay, if you consider this system, now for this system we can write, you see, if we put it together, we can write it like this. So basically, if one defines A to be the matrix Aij, right, the matrix Aij, so this would be a n cross n matrix, that is n cross n matrix, then star may be written as A u equals to B, where A is B cross n cross n matrix, this is given. Okay, B is a n cross n vector, okay, and U is a n cross n unknown vector. Clear? We can write it like this. So basically this can be written in short form like this. This we already know. And the thing is, if b equals to 0, we call such a system, we call the system as we call it a homogeneous system of equation if b not equals to 0, then it's called inhomogeneous. Inhomogeneous system, right? Okay, so we are going to need a very important theorem here, and this we are going to use in a lot of different places. Okay, so theorem, I am not going to prove the theorem, you have to do it yourself. The theorem is quite easy to prove. So the system star has a unique solution, okay, if and only if determinant of A is not equals to 0, right? Okay, so that is quite true, right? And we can also say, so alternatively the homogeneous system so B equals to 0, okay, homogeneous system has only trivial solution, okay. So trivial solution means U is equals to 0, identical equals to 0, then determinant of A has to be non-zero, okay. So if A is non-singular, then you have a unique solution and vice versa, okay. The proof, I am not doing the proof, this is very easy to do. So proof, please check this, proof, please check this, okay. And we are going to use this theorem, okay. So now let's look at a small property of determinants which you are going to need. So you see, first of all, let's say that we assume, let's say, okay, so now consider this, consider A of x. So I am writing a matrix A which depends on a variable x, right? And this matrix is given by Aij on x. So you can write it as a, for now let's just write it as an n cross n matrix. You can of course write it as an n cross n matrix. So you have that every coefficient is a function of x, clear? So consider this where Aij is from, let's say, R to R, okay. It can be from AB to R, but okay, let us just do it right this, AB to R, AB to R, clear? Okay, so this is given. Now the thing is, you see the set of all, so if you are writing like this, R continuous, this is I am assuming, right? Okay, then the function is called a matrix valued function, okay. So then A is called a matrix valued function, okay. So a very simple example you can think of, a example, let's say A, I am defining it to be x 0 1 2, let's say, okay. So you see this is, it's not a constant function, constant matrix, because there is a variable x, okay. And let's say this x is in 0 and 1, okay. So now this matrix is not a constant matrix but a variable matrix A of x, right? So that is a matrix valued function, okay. Now, so there are properties of this function, okay. Before doing the properties, let's just write it down. See, the space of all continuous matrix valued functions, matrix valued functions, okay, we are going to define it like this. In AB is denoted by so we will write it as C n cross n size matrix, okay, of AB, CAB. So CAB is the set of all continuous matrix valued functions on AB, right? Okay, and if for all, okay, how am I defining it? If for all AX, BX in C n cross n AB and alpha in R, we can do this. You see, A plus B, okay, acting at X is Aij of X plus Bij of X, clear? And alpha times A acting at X is nothing but alpha times Aij of X, okay. So that is that. So with those two properties, we define a new space here, the space of all continuous matrix valued function. We denote it by Cn and n. And what are the operations? The operations are natural operations, but it just depends on X, okay, right. Now one may define, okay, C n cross n. How do I write it? Maybe here, n cross n of AB, okay. And then let's say M. What is M? M is the mth derivative, okay. So basically this is the space of all M. M is in n, that is M at times continuously differentiable functions, okay, continuously differentiable functions, okay, in A, B, okay. So is this clear? I think this is okay. Okay. Matrix valued functions, of course, matrix valued. Consider matrix valued. I forgot to write matrix valued. Okay, let me put it this way. Matrix valued. Okay, now what we are doing is going to the thing is, how do you define such a thing? Okay, and is defined as, so are defined as, and is given by A prime of X, let's say. How is the derivative defined? A prime of X is nothing but Aij prime of X, okay. So this is how we define it. Now you see, let's say that I want to write, first of all, let's say I want to talk about the determinant of Ax. So basically, given a matrix Ax, so basically let's say Ax, now given, this is very important, we are going to use this thing in C M n cross n. The notations are quite a little complicated, so we have to keep that in mind. So you see, what specifically this means is we are looking at n cross n matrix, okay, where every entry is at least is m times continuously differentiable. That's what it says, nothing special, okay. And the functions all are defined on AB. That's what, okay. So if we are starting with Ax, which lies in this space, and then what happens is, determinant of Ax. How do you find it? Determinant of Ax is nothing but summation j equals to 1 to n. If you know that aij of x, alpha ij of x, right? Yes, we can write it like this, right? And over you see this alpha ij of x, so essentially this will be your cofactor, right? Cofactor, where alpha ij of x is the cofactor of aij. Okay, right. Now once that is true, you see we want to find out, then we want to write down what is del determinant of x del aij of x. Okay, then if you do that, this is nothing but alpha ij of x, right? Okay, it follows easily because every other thing is becoming 0 and the only thing which is remaining is alpha ij. Okay, so and hence and therefore and so you see determinant of ax, the if you take the derivative of the whole thing, that will be nothing but, okay, a11, if you write it properly, a11 of x, a1 n of x, the derivatives. Okay, the second will be 2 1 of x, a2 n of x, a n1 of x, a n n of x. Okay, plus a11 of x, a1n of x, and then a n1 of x, a nn of x. So basically you understand the we are doing like the derivative thing, like the Leibniz rule kind of thing, but only in the rows. So the first row gets derived in the first thing, the first row is derived, leaving intact all the rows below, and then the second row will be derived, every other thing will remain intact, and we go on till the nth row. This is what you do. Okay, so this is how you take the derivatives of a matrix valued function. Okay, so the determinant of the derivatives of a matrix valued function. Okay, so this is quite clear. If you are still doubtful, you please so check it using a 2 cross 2 matrix. Okay, then you will be convinced. But this is quite clear, right? This is quite clear. Okay, so with this we are going to end this video.